about surface haptics today. In particular, I will focus on electro-vibration. So there are different ways of displaying tactile effects or haptic effects. Oh, thank you. Tactile effects or haptic effects through the touch surfaces. But today, I will be more focusing on electro-vibration. And another thing that I want to mention is I will talk about the science of electro-vibration. Maybe this conference is, as Han calls, like an industry-facing kind of conference, but I'm really excited about the science part of electro-vibration, so that's what I'm going to talk about today. I had the same excitement when first the Phantom device came out, like almost how many years ago? I guess 25 years ago. Well, how long was it? Yeah. I worked with the second copy of the Phantom device almost 25 years ago, and I was very excited about the technology at that time. Now I'm very excited about the surface haptics as well. So I'm pushing for it, and I hope that it will be the killer application for the community. All right, so let me move on. So when we talk about surface haptics, there are three ways. In my mind, that there are three ways that you can use to display tactile effects through the touch surfaces. Right? One of them is like vibrotactile actuators, vibrotactile actuation. So you can use like simple vibration motors or piezo actuators to display vibrotactile signals through the touch surfaces. This is very common. And it's a low-cost option. And the second way is, which I'm going to talk about, is electro-vibration. So another way to display tactile effects. So if you take a capacitive touch screen, this is something that you use on a daily basis with your cell phone, your tablets, and other devices. And if you apply a voltage to the conductive layer of that capacitive screen, then you create electrostatic forces between the finger and the surface of the touch screen. So that's the second way. And the third way is this ultrasonic actuation. So again, like if you take the piezo actuators you're using for vibrotactile feedback and actuate them at ultrasonic frequencies, then there's a squeeze film effect happens. So there's a small air gap. Because of the air pressure, small air gap occurs between your finger and the touch surface. So if you modulate that, if you turn it on and off, you can create tactile effects on the surface. So if you turn it on, then there will be an air gap, which means the friction is reduced, right? And if you turn it off, then again friction increases, which is the opposite. Which is the opposite case with electro-vibration. When you turn on the voltage with electro-vibration, you create additional frictional effects on the surface. Right? So you increase the friction between the finger and the surface when you turn on the voltage in the case of electro-vibration. And if you turn it off, since the surface is already very smooth, typically the touch screens have a very smooth surface, then you will have less friction. Okay, so today, that's what I'm going to talk about, this electro-vibration, the physics behind electro-vibration, and also the tactile perception problem. Alright, so again, as I told you earlier, so this is the touch screen that you have, right, which is made of typically three layers. So if you look at it here, the base layer is the glass plate, and on top of the glass plate there is like a conductive layer. And then on top of the conductive layer, you have an insulator. Right? But typically, the conductive layer is an ITO, indium tin oxide. And typically, the insulator layer is isum oxide. So similarly, on the other side, on the finger side, the stratum corneum, the outermost layer of your finger, serves or acts like an insulator, and the inner layer serves as a conductor. All right? So if your finger is not the principle, the electro-vibration works because your finger is also conductor. So what happens in here, if you look at it, this diagram in here, so you have conductive layer on the touch screen side and conductive layer on the finger side. So you have this parallel plate capacitor effect. So if you apply voltage to the conductive layer of the touch screen, then you have this parallel plate capacitor effect, right? And this is how you generate the electrostatic forces between the finger and the touch surface. So once you have this attractive electrostatic force, which is represented as Fe in this diagram, effectively they increase the force in the normal direction. So as a result, the friction increases, right? So these are all the time some attractive forces. Why they are attractive all the time? Because when you apply like alternating voltage to the conductive layer, so the voltage goes from positive to negative, negative to positive again. So when you have the positive voltage in here, your finger is charged with the negative charges. Your finger is polarized with the negative charges, and the surface is polarized with the positive charges. So there's an attractive force. So when you have the negative voltage in here, this time your finger is polarized with positive charges, and the surface has negative charges. So there's always some attractive force, small attractive force between your finger pad and the touch surface. So this force is so small that you don't actually feel it when you try to touch the screen. But as soon as you start sliding on the screen, you feel it in the form of a frictional force, okay? And that feeling is quite prominent. Alright, so what do we know about it? Like one thing we know, if you think about this as like a parallel plate capacitor model, so this force, this electrostatic force, is a function of the square of the voltage. We are sure about it. Again, like if you use the model of the parallel capacitor model, parallel plate capacitor model, then this force is a function of area. Okay, and this force is also a function of the interfacial gap between the finger and the surface. Okay, so the gap between the air gap between the surface and the finger as well. Again, as I told you that this causes an increase in the normal force. As a result of increase in the normal force, you can see that in here, I have a friction coefficient, so mu times the new normal force, I have the tangential force. It looks simple, but actually it's not. That's what I'm going to talk about. Alright, so let me show you first of all this animation, nice animation showing how the principle works.
Signal applied to the transport electrode displaces charges within the insulation layer, creating an oscillating electric field. When a finger is placed on the surface of the touch panel, a periodic motion of electrical charges is induced at the tip of the finger. This results in a periodic attraction force between the finger and the panel, modifying the friction between the sliding finger and the panel, and thus producing a sensation of tactile texture.
Okay, I like this animation. I think it summarizes what's happening. So we were interested in the physics behind it and also the tactile perception, because there are really interesting problems. But before moving on to that, what could be the applications of this technology? So I mean, like, these are probably the applications of the surface haptics, right? It could be applied to the other, like ultrasonic actuation or vibro-tactile actuation as well. So one application I'm thinking that could be very exciting is this online shopping application. So maybe in the future, we're not going to just select the size of and the color of the clothing that we're buying online, but we will also maybe choose based on their textures, right? Especially if you can add the softness, feeling of softness. Currently, we can simulate the roughness, feeling of roughness, but if you can add the feeling of softness, then I think the online shopping could be a very nice application for this technology. Again, some other applications could be like education, touch. Again, I want to emphasize that like softness is probably very important in here. And one very promising application in my mind is aids or user interfaces for blind. So using friction, because I can modulate the friction on the surface, I can display shapes on the surface of the touch screen. and that enables the blind people to feel shapes and to appreciate some graphical information, like bar charts or pie charts. So currently the only interface for blind people is the Braille alphabet, right? They can read text using the Braille alphabet, but they cannot really feel shapes or objects they see on the screen. Well, they don't see on the screen, sorry. Another application could be in the automotive industry or in general tactile user interfaces. As you know that nowadays many companies are moving to they want to convert the whole front panel to touchscreen-based interaction panels. And what they are missing is again tactile feedback in here. And tactile feedback, especially in the form of friction modulation, could be very helpful for this purpose. In entertainment could be, I have to move it down. So entertainment, sorry about it. Entertainment could be another application. Imagine that like you're playing Angry Bird game and then you're feeling like let's say you're pulling the slingshot and you're feeling the stretch effect. I think it will be more engaging and more exciting. So I can easily increase the number of applications and talk about more, but I guess I have a limited time, I should move on. So as I told you earlier, this is the area that we are quite interested in right now, is the science behind the electrovibration. And if you look at it, it's a really interesting topic. So this diagram shows the pieces of it. So this is the part that we are zooming in. You can see that this is the interaction between finger and the touch surface. So if you look at it, this is the cross-section of the touch screen, 3M touch screen, capacitive touch screen. You can see the glass in here. On top of we have the conductive layer, ITO layer, and then on top of that ITO layer, we have the insulator layer. And here, understanding the contact mechanics is one issue, but another thing is better understanding of tactile perception is another, seems like an interesting problem. And we already know that tactile perception is driven or governed by this 4-channel theory, and there are 4 receptors mainly responsible for the tactile stimulus, and we are interested in how they respond to the friction modulation. So the problem is interesting in the sense that, if you think about the parallel plate capacitor model that I mentioned earlier, in that model there are several assumptions made. Right? One assumption is you always think that the gap between the plates is constant, which is not the case in case of interactions between finger and the touch surface. Another important issue is the plates are flat, right? But in case of finger, if you think about the finger roughness significantly affects what you're feeling. So it has a multi-dimensional, multi-scale roughness problem. So this diagram showing the roughness spectrum. X-axis is the wavelength, and the y-axis is the roughness. So you can see that it has a different roughness behavior at different landscapes. So that's something very important. It turned out to be that this is something very important for the electrovibration because it significantly affects the real contact area. Okay, so that's something I'm going to talk about. So throughout my talk, I will emphasize 2 different areas. One is the apparent contact area. This is something that we see if we put a camera under the touch screen, so we can easily observe the apparent contact area. And the other area that I'm going to talk about is the real contact area. And our results, our studies shows that electrovibration changes the real contact area. It increases the real contact area. And what is the real contact area? It is again related to this roughness spectrum. So when the finger makes a contact with the touch surface, if you look at it, the topography of the finger, you easily see the ridges and grooves, but if you zoom in further, then you see many other scales as well. So when the finger makes a contact with the surface, those points make atomic contacts, and that's what the electrovibration does. So it increases those atomic contacts. Okay, so as I told you, like my talk is going to focus on contact mechanics and tactile perception related to electrovibration. So I'm going to talk about the studies that we have done, experimental studies that we have done. So we hooked up with a group from Belgium in 2017 in Haptics conference in Germany, and then we conducted some experimental studies. They had this nice setup, robotics-based imaging setup that they have developed earlier in 2014, and we basically inserted our touch screen in here and our code in here. So we have conducted some studies, experimental studies in them. So let me show you the animation in here again. So this is a setup, basically, like you can see on the right hand side, this is the camera system, which is used for imaging the fingerprints. And you can see the white color piece is the robotic system, which helps you to adjust the normal forces. So normal contact forces. And there is like two force sensors, one on this side, the other on the other side, which enables to measure the contact forces, both normal and tangential forces. So you're measuring normal forces, and using a simple PID controller, you adjust using the robotic system and the PID controller, you're adjusting the magnitude of the normal forces. So keeping the normal forces constant is important. Alright, so look at it now, the images captured in here. I mean, you will very quickly, so this is the apparent contact area that I'm talking about. So the purple line defines the apparent contact area. So area inside the purple line is the apparent contact area. And you can see some dots in here. These are due to the ridges, right? Finger ridges. And sometimes people call that ridge area, which is approximately 40 to 50% of the apparent contact area. But interestingly, real area is even smaller than the ridge area. So it's approximately like 1% of the apparent contact area. So it's a very, very small portion of the apparent contact area is actually the real area. So here what you will see in this animation, that as the finger moves, so using this robotic system, the finger is stationary and the touch screen below the finger moves in the tangential direction, and the user feels the additional tangential forces when you turn on the electrovibration base. So I want you to pay attention to the animation here. Look at the area, the apparent contact area, one more time. What do you think? Is it increasing, decreasing? Can you visualize it? Huh? What do you think? Is it increasing or decreasing? Decreasing. Isn't that surprising? So, I mean, it's very interesting. Like, so when you turn on the electrovibration, the apparent contact area is reduced. So that was a surprising result for us because, 3 minutes, wow, okay. I was very slow. Sorry about that. So, I mean, like, maybe I should keep it short. So it was very, very surprising for us because, you initially think that the area would be very important, but which area is the question. So apparently the apparent contact area is reduced. So, as you can see, like friction, so the blue curve shows the case where the electrovibration is off, and the red curve shows friction curve shows when the electrovibration is on. So this is the friction as a function of finger displacement. So you can easily see that it's a typical friction curve, and the red one is above the blue one, which means that the friction is increasing, right? This is something we are expecting. But look at it again. You can see the adhesive effect in here at low normal forces. The friction is more significant. As you increase the normal forces, the friction saturates and then reaches to some steady state value. This is also known for finger touchscreen interactions, I guess. But the surprising results in here, you can see the red bars are showing the time, the case when the electrovibration is on. So this diagram is showing the reduction in apparent contact area. So you can see the red bars are higher than blue bars. So it's indicating this is the percent reduction in apparent contact area. So it's obviously, very clearly, apparent contact area is reduced. So what happens then? So how do we feel an increase in friction? Okay, so if you look at this problem a bit more, so there's a nice piece of work done by Adams et al. So the tangential force is driven by the simple formula. The tau in here is the shear stress. AR is representing the real contact area, right? And Adams et al. Suggests inserting the simple relation for the shear stress. Tau 0 is some constant value, so it's called intrinsic shear strength. And alpha is another constant, pressure coefficient. P is the pressure, and you insert for F divided by real area again for the pressure. And then you end up with something like this. So if you focus in here. So in the case of, like if you compare the cases of electrovibration off and on, you can see the normal forces are the same, right? This is the normal forces applied by the finger. So if you assume that this part is also constant, and alpha is also constant, you can easily see that a real area, real contact area, seems to be the one responsible for increasing tangential forces. Alright, so we came up with this idea. My PhD student came up with this idea, and he keep saying that this must be something to do with the real area. But of course, as I told you earlier, you cannot really measure the real contact. It's impossible to measure because you make this like micro contacts. So then we start looking at the literature whether there are any models, on that topic, and we hit some of them. So this is one of the models developed by a person. Bo is our collaborator right now, and we came up with his studies on multi-scale contact modeling, and it was very interesting. I mean, like you guys probably heard about Hertz's contact theory, like if you work in the area of contact mechanics, well known. But again, if you are in the area of contact mechanics, person's contact theory is also well known. So we do know and we learn about it. And we start collaborating with the Bo person. He works for Zurich, IBM Zurich Center. And we came up a model explaining the interactions during sliding under electrovibration. So I'm going to talk about this part and then I will stop talking. So this, you can see in here, this is the first diagram showing the friction force as a function of normal force. You can see these points are the experimental data, right? And the solid lines are the model fitting. And again, on the right-hand side is the same thing. So x-axis is representing the normal force, y-axis is representing the friction coefficient. Again, you can see the adhesive effects in here. So friction coefficient is not really a constant value. It reaches to a constant value. But how do I understand there are some adhesive effects? Like if you look at it, the coefficient of friction at low normal forces, adhesion seems to be a significant factor. And what else we see in here, as you increase the voltage, you can see the tangential forces are increasing, friction coefficient is increasing, all because of the reason of this increase in real contact area. Okay? So, I have more slides. I was planning to talk about tactile perception, but I guess I went a little slow. But you're welcome to talk to me after maybe the session. We can have a one-to-one chat. So two important things in here is apparent contact area is reduced, but real contact area is increasing under electrovibration. Thank you.